Hello everyone, my name is Sahil and today I'll be talking about this work on online discrepancy with Recourse for vectors and graphs. This is joint work with Anupam Gupta from CMU, Vijay Krishna Gulunathan, who just started his PhD at Stanford, Ravi Shankar Krishnaswamy from MSR India, and Amit Kumar from IIT Delhi. So let's start by recalling the classical discrepancy minimization problem for vectors. So this is known as the vector balancing problem. You're basically given a bunch of vectors, capital T vectors in n dimensions. So to keep these parameters in mind, n is the number of dimensions and capital T is the number of vectors. And you should think of n as being some small number, like say 5 over 10, but capital T is very large. So there you have many, many vectors. Each of these given vectors have L infinity norm at most 1. So imagine them in some cube. Your goal is to assign them some colors, which are plus or minus ones. So you assign each vector, either keep it as it is or you flip the vector by assigning it a -1 color. So as to make sure that the signed sum of the vectors, the sum of the vectors after the sign, that has small L infinity now. So this signed sum vector, I'm also going to call it the discrepancy vector. So this is the discrepancy problem, minimization problem, where you just minimize the sum of these signed vectors. So this is a very classical problem. So as you might notice already, like in one dimension, the problem is easy. And you are given a bunch of scalars, so you can just greedily color them to make sure that the discrepancy is small. But already for 2 dimensions, the problem already becomes non-trivial. So if you do something like random coloring, in expectation, it sounds good because each coordinate has expected value 0 because each sign is basically plus minus 1, expectation is 0. However, because of variance, and because of union bound over these L coordinates, you get some bounds which are roughly square root t square root r. So this square root t is not good. We don't want to lose polynomial in t, and we want to do like something like either like independent of t or maybe polylogarithmic in t, because t is large. So what's known for this problem? So this is like a very classical problem, the offline vector balancing that I just told you. There are generalizations of this problem, the Beck-Fiera, Noesch, and even problems of this problem has been studied for other norms. I'll not get into those generalizations today. There are many, many applications, including fair divisions, randomized control trials, scheduling. It's a very basic problem in discrepancy theory with multiple books written on this topic. And so for the offline problem, where you know all these vectors, there's some classical results which basically imply a square root n bound on the discrepancy. So notice n is very small, n is just the number of dimensions, like 5, 10. So this gives a very strong and it's also known that you cannot hope to do better than square root n. And there are some omega square root n lower bounds as well. So okay, so the offline problem in this setting is pretty well understood. The question that we want to study is what can we do online? So basically, online means these vectors arrive one by one to you. As soon as a vector arrives, you have to immediately color it. You have to assign it a plus or a minus sign without knowing the future vectors and still trying to minimize the total discrepancy. So ideally, again, you want dependency, like say polynomial n is fine, but we want it to be like either independent of t or logarithmic in t, polylogarithmic in t, the number of vectors. However, as you might already start seeing that there are already very simple counterexamples which show that polylogarithmic in t is impossible. The idea is that the adversary can keep presenting you the next vector. An adaptive adversary can present you the next vector, which is orthogonal to your current discrepancy vector. So whatever is your current sign sum, after you've assigned these vectors, some coloring, the next vector would be orthogonal, and then the norm of your vector, the L2 square, basically say keeps increasing, and hence you'll have to lose a polynomial in t in the total discrepancy, like omega root t, which is not good. We want it independent of t or like maybe polylogarithmic. However, there are some recent results where they assume something about the adversary. In particular, the adversary is not fully adaptive. Either the adversary is stochastic, maybe the vectors are being drawn from some distribution, some underlying distribution, or maybe the adversary is oblivious, like it cannot see what colors we've assigned till now. So one has to make some assumptions, and then maybe polylogarithmic in t guarantees are possible, which have been shown in these recent works. But we are really interested in this work in handling both adaptive adversaries. We want to study like a fully dynamic setting where the adversary is adaptive. Moreover, the vectors could also depart. So there are some applications, for instance, in scheduling, where you might imagine that some jobs arrive, they stay in your system for a bit, and then they depart. So departures are also happening. The question is like, okay, can we still obtain any guarantees for online settings when you have both arrivals and departures? And the maybe arrivals and departures are both fully adaptive adversary. And one can already show even like for some random departures, I mean, you have to, in some sense, recolor the vectors. If you don't change the colors of old vectors even, then you cannot do much. You have to lose polynomiality. So this brings us to the online discrepancy with recourse model, where again, you get these vectors or like they arrive or depart in each time step. This time you are allowed to recolor some of the old vectors as well. You want to keep the discrepancy small, but you don't want to change too many old colors. So you want to minimize get the best discrepancy while minimizing the recourse, which is the total number of colorings over total time step. So the amortized recourse. And I mean, this is not the first problem. There have been many, many problems that have been studied in this online problems, which have been studied in this recourse model. So I'm just listing out some of the problems. There are many, many references. I would suggest you to look at the paper. But we want to study this problem in this discrepancy setting for this fully dynamic setting. So can we get basically a poly n times polylog t bound in the discrepancy with what's the minimum recourse we want? And naively, okay, of course, order t recourse suffice, where in each time step you can always recolor all the existing vectors, but that's not what we want. So our main result, the first main result is that, okay, for this fully dynamic vector balancing problem, we can actually get the optimal discrepancy, like the square root n discrepancy, which is the best possible even in the offline, using linear recourse, roughly linear recourse, linear in the number of dimensions. So order n log t, which is much, much better, which is exponentially better than the trivial bound of order t. Okay, I mean, and we also have some results in more general setting, but I won't get into them right now. And the proof is based on some Barani-Greenberg, which I'll talk a little bit more. We also have another result on some kind of a special case, you can say, of the problem, which is the graph balancing, the edge orientation problem, also known as maybe the graph balancing problem, where we can get even better guarantees, but I'll get to it like later in the talk. So let's first look at what can we do for the vector balancing, or like how the proof goes. So the proof basically goes by generalizing the Barani-Greenberg offline algorithm. So what's the Barani-Greenberg idea? So this is the offline setting. So you're basically given these vectors, you want to minimize the L infinity norm. Roughly what they achieve is that they reduce the capital T number of vectors to n vectors. So notice capital T could be very, very large, whereas n is small, like 5 times. So their main idea is some kind of a reduction from capital T to n, and it's basically based on a LP relaxation. So you write the natural linear program for this problem, where you assign a variable xt for the tth color. You put a constraint that summation over t xt vt equals 0 for all the coordinates. Notice these are just n constraints. So what this implies is that if you look at a basic solution, a corner point, then most of the colors will actually be either plus 1 or minus. So you'll have like many of the box constraints which will be tight because there are only n other constraints. So even if all of them are tight, you'll still get at least capital T minus n integral colors. So that basically is the idea that, okay, you solve this basic solution, all the integral vectors, you already fix them. And for the remaining n fractional problems, you continue solving the problem. So in some sense, you've reduced the capital T vectors problem to an n vector problem. And now once you have only n vectors left, then you can maybe do randomized coloring, or you could do Spencer or like more complicated things to get something which only depends on n. So you've basically gotten totally rid of T, dependency on T, the large T. However, the challenge in extending this approach to the online settings, in the fully dynamic settings, is that the basic solution can change drastically when you add or delete a vector. So there's no a priori guarantee on how many coordinates will change. Even if you add just one vector, maybe the basic solution totally changes. So there's no guarantee on the recourse. So how can one extend it? So we basically achieve some kind of you can think of like a distributed Barani-Greenberg algorithm, where the underlying idea is actually very clean. Like the idea is just you think of like embedding all the vectors in a complete binary tree of height log t, where the leaves correspond to roughly 2n vectors. So you just like arbitrarily partition these vectors into 2n blocks, 2n vector blocks, and put each of these 2n vector blocks at a leaf. Now apply this Barani-Greenberg algorithm that we saw on the last slide to reduce 2n vectors in a leaf to n vectors. And these n fractional vectors that you have, think of them as upgrading them to your parent. So each leaf basically sends n vectors to their parent. Now notice these second last level nodes, they are getting nn vectors from each of their children. So they'll have again at most 2n vectors. Again, they apply Barani-Greenberg, so they reduce these 2n fractional vectors to n vectors, which n fractional vectors, which they send to their parent and so on. So you keep applying this thing. At the root, you'll be left with like some small n fractional vectors, and for which you can just run some offline. Now, what's the benefit of such an approach? The benefit is that in some sense, each arrival and departure can only affect a small number of nodes in the graph. It won't affect the entire solution. So you won't have to solve Barani-Greenberg from scratch for the entire set of vectors. More formally, like the idea is that each deletion only affects a single root leaf path. So you only recolor the vectors which belong to this root leaf path, which are only like order n log t. So that's just the idea. It's very clear. And I mean, you can work out the missing details, but that's basically how it goes. So this already gets us near optimal discrepancy with linear recourse, linear in the number of dimensions times the logarithmic in t. So now let me give you a high-level idea of the edge orientation problem, which is the other result that we get. So what's the edge orientation problem? So here, imagine you're given a graph. You're basically given n nodes of the graph, but the edges are being dynamically inserted and deleted. Each time an edge is added or deleted, I mean, you have to orient the edges. So by orient, I mean like either point the edge from U to V or V to U, while minimizing the sign degree of each vertex. What do I mean by sign degree? It's the number of incoming edges minus the number of outgoing edges, the magnitude of that. So you want to make sure that each vertex is nearly balanced, like incoming and outgoing degrees is nearly the same. So that's the problem. So edges arrive and depart, and you have to orient them. So this can be shown, like I won't show the reduction, but basically this is a special case of the problem on the vector balancing problem, where you have two sparse vectors, where you have all the zeros and only two coordinates have like 1 and -1, and then you can basically capture the problem, capture this problem. So what's known for this problem? So since this is a special case of the vector balancing with sparse vectors, in the offline setting, we already know Beck-Fiala results, which gets us constant discrepancy. There are also like some alternate algorithms, but Beck-Fiala is one big hammer. However, it's not clear how to apply this thing in online and especially in a dynamic setting. So the main result that we are still able to achieve is we get nearly like a polylogarithmic discrepancy, which is you can think of like a constant O tilde1 discrepancy with O tilde1 amortized recourse. So polylogarithmic guarantees both in the near optimal discrepancy and very small recourse. So that's the main result. So notice this is much better than the results we got for vector balancing, where we were needing the recourse to be roughly linear in n, whereas now we only needed polylogarithmic in n. And the high-level idea of this result goes in two steps. In the first step, we decompose the given graph into a bunch of disjoint expanders. And in the second step, we apply some kind of a local search solution to each of these expander pieces. So that's the high-level idea, and I'll go say a little bit more about both these steps. So let's first look at the second step. Like I claim that for this edge orientation problem on an expander, local search is already a good algorithm. So what's the claim? So first of all, what's the local search algorithm? It basically just flips, you initially arbitrarily orient the edges, and then you flip any edge UV. If flipping it decreases the max of the discrepancies of the vertices. And the claim is that if you reach a local optimum to this solution, that already gives you a logarithmic discrepancy, so which is already very good. You're not getting polynomial. For simplicity, I'll assume regularity. Right now that the original graph is regular, these results also extend to nearly regular graphs, which you can find them in the paper. So the proof idea is the following: that consider like the local optimum and look at the vertex, which I call the root, which has the highest discrepancy, the highest magnitude discrepancy, k. The claim is that because you are at a local optimum solution, all its neighbors in particular, the vertices which send an edge to this vertex, they should also have a relatively large discrepancy, at least a discrepancy of k-2, otherwise you would have flipped this edge. And similarly, like this is the first layer. Now, if I go 2 hops away from the root, then they should have a discrepancy of at least k-4, because otherwise, again, you would have flipped from k-2 to k-, like from layer 1 to layer 2, that edge, and so on. The interesting power of expansion is the following claim that the number of edges incident to the first I layers. So let Si denote the set of nodes. which are at most I hops away from the root node, then the number of edges in the induced subgraph of Si, one can show via expansion properties of the expander that this number of edges, that increases very fast. In particular, in each type step, it increases by some factor like 1 plus v over 3. So why this is powerful is because the total number of edges in your graph is just n. So hence, you can only go roughly like logarithmic in m number of steps. After that, you'll already exhaust all the edges. So you're going, basically in each time step, your discrepancy is only decreasing linearly, but the number of edges are increasing exponentially, and hence you cannot have more than logarithmic steps. That's the step, main idea, and like, yeah, you can work out the details. And also let me remark that, yeah, expansion is necessary. Like it's known in general that for general graphs, local search actually gives you very bad solutions, can potentially give you very bad local optimums. Good. So this gives you a simple algorithm on expanders. I mean, one could also have applied Beck-Theory, but this expander algorithm, this combinatorial algorithm is more important for us because of the other step where we do the dynamic expander decomposition. So first, let's recall, so what static expander decomposition is, where the graph is fixed and you just decompose it into a bunch of disjoint expanders. So there are many results known in this way, starting from the works of Dan Spielman and Shamuateng for Laplacian solvers. So this thing is very well understood. When the graphs are fixed, you can basically decompose it into a bunch of disjoint expanders, 1 over polylog expanders. Turns out even in dynamic graphs where your edges are being inserted and deleted, you can still get some kind of a dynamic decomposition. So first one shows that, okay, insertions are easier to handle, so one has to only worry about deletions. And for deletions, one argues that it's actually true that the expanders do not change very drastically. In particular, after like say I operations, I insertions or deletions, only linear in I number of vertices will have changed, but their edges will have changed. So it's not that the expanders are changing drastically. However, we are still not done, because although the expander graph might be slowly changing, the local optimum for the discrepancy could have drastically changed. So notice that we need to also find a solution for this new expanders that we are constructing. So that could have drastically changed, but using some kind of a gradual removal of these delta p edges, this pruning removal edges, one can show that actually you can actually reuse your old local set solution and gradually converge to this new local set solution and pretty fast. So that's in some sense, step 3 is most of the technicality, but I won't be able to go into the details. Good. So let me just conclude. So what we saw at this talk, first was the dynamic vector balancing problem, where we obtained near optimal discrepancy in roughly O tilde n recourse, where n is the number of dimensions. And the idea was some kind of a distributed Banani-Greenberg. For the edge orientation problem in the dynamic setting, we get near optimal discrepancy and near optimal recourse using the expander decompositions and local search. The main open question for this work are, first of all, the vector balancing problem. Can we get near optimal discrepancy using much smaller recourse, like O tilde 1 recourse? So I mean, one can show that, okay, you need at least some recourse. Can you do it even like in nearly constant recourse or even like root n recourse? And so the other open question is, can we obtain more results generalizing the edge orientation problem? So these are sparse vector settings, like the Beck-Theory setting. So for these sparse settings, it's plausible that the right answers are much better. So can we obtain them for these problems, like for beyond sparsity too? Thank you.